finish 4.6, which we only just got started with, let me remind you about the exponential growth for doubling times formula, which is if you've got some initial population. So remember in 4.6, which I'll put at the top here, this is 4.6 continued. 4.6 is all about applications, meaning real world problems. And I'm focusing on the population growth problems, just because it seems like most of this class, you guys are more leaning towards biology majors than chemistry or physics. So, okay. So for the function n of t equals, so I'm leaving space here because I'm going to write what each of these pieces means up above. It's the initial size n naught times 2 raised to the t over a. So initial population is that n sub 0. So it means like population n at time 0 is how you could think of that. Or it's also often read n naught, not as in like the initial size. Doubling time is a. So that's what that little a term is. Time, of course, just time that passes for this model is t. And these should be measured in the same kind of time, you know, both in years, both in minutes, both in months, whatever it is, they both need to be measured in the same kind of time. Okay. And then n of t then is going to be, excuse me, whoops, I'm writing this backwards. That's okay. Size of population after some time, after some given time t. Whatever the t is that gets plugged in. So this is just a generic one with just t in there. And if you wanted to know the size of the population after 6 months, then you would plug 6 into the function, and this would output the size of the population after 6 months. Okay, so we already did an example with bacteria population that was doubling every 3 hours. Let's now do a rabbit population, which does not double quite as quickly, but still does double pretty quickly relative to other mammals. Okay, so we have a current breed of rabbit was introduced onto a small island 8 months ago. So maybe you've heard about these things that happen where species are introduced that are not native to a place, are introduced and they sort of take over because they're able to reproduce so quickly. And it can be a problem. Like, it's so much of a problem that there are laws that prohibit people from bringing in non-native species into certain places. The current rabbit population so this happened 8 months ago, and now the current population on the island is estimated to be 1,800 rabbits. No, sorry, I'm reading the wrong number. Sorry, I was like reading a different problem or something. 4,100, and doubling every 3 months. Okay, so we're seeing some key things here. I'm seeing that doubling time. That to me is telling me that A should be 3. Okay, and T is just time. Like, T is going to pop up after they ask me for some span of time. But what's the first question? The first question is, what was the initial size of the rabbit population? So they're not asking me for time first because I don't know the initial size. And what am I talking about here? Because you might say, well, what about the 4100? That's not the initial size. That's the size after 8 months. So there are two other parts to this problem, parts B and C, but I'll actually answer part A first, and then we'll get to part B and C. Okay, so what's going on here? I've got a breed of rabbit was introduced 8 months ago. So some number of rabbits were introduced 8 months ago, but I don't know how many. But I do know that currently there are 4,100 rabbits, and they double every 3 months. So what do I have just straight off the bat? I have that A is equal to 3. So I know that the model should look like, this function formula should look like this. I don't know n naught. And then 2. Why is the base 2 for this formula, by the way? Because this is all about populations that are doubling, right? We're given information about when they double. An exponential function that has a base of 2, you can think of as like a doubling function. Okay. And then t raised to the 3. So that's all I know so far, is that A is 3, because that's the doubling time, 3 months. Okay, but I need to know n naught. I need to know n naught, but I also know that according to the problem, after 8 months, there are 4,100 rabbits. How do I put that in terms of like function notation here? Let me write it down in words. After 8 months. So are there any ideas about what I could do here with that information? So I know that t would be 8, right? Because that's a time. So n of 8, the population after 8 months is 4,100 rabbits, right? That's what this model does. It tells you, give it time and it outputs a population. Okay. All right, so how do I translate this into something that can be worked to be able to solve for n naught? Well, I would say n of 8. Oh, sorry, 1 second. My computer's doing some. Okay. N of 8 means this function here with 8 plugged in for t. So I would say n naught times 2 raised to the 8 over 3. That's what this means, n of 8, right? And then is equal to that number, 4,100. 4,100. So I'm taking this statement that's in words. After 8 months, there are 4,100 rabbits, converting that into like a function statement after 8 months. So the population at 8 months or after 8 months is equal to 4,100. And then now taking this and applying it to the model here that I have, the like unfinished model, and just interpreting it from this form into this form. And all I'm doing is saying n of 8 just means this thing here with 8 plugged in for the letter t. That's literally all it means. So that's what I've got here on the left side, and then of course still equal to this number, 4,100. So now all I need to do is figure out, well, what n naught is. So n naught is going to be 4,100 divided by 2 raised to the 8/3, because this is connected via multiplication right here. So I can just divide this whole thing over. Yeah, it looks crazy, it looks messy, that 2 raised to the 8/3, but it's just a number. So I can just divide it all the way. It's a number attached to this via multiplication. So just divide by both on both sides. And then n naught will be, so let's say 4,100 divided by, I'll wrap it in parentheses just to be safe, 2 raised to the, well, need another parentheses for my exponent, 8 divided by 3 up in the exponent position, close both parentheses, and I'm getting, I'll say approximately, Book rounded wrong. Hang on 1 second. Did I plug something in wrong? No. Yeah. Why did they round down? Whatever, we'll do that too. They rounded down for some reason. Like I'm following along in the example here. They got 645, but I mean, you can see that should be 646 if you rounded, because that's a 0.7. I'm not sure why they did that. Maybe it's just a mistake. Anyways, we'll do what they did too, though. We'll just kind of pretend that that's what it would have rounded to. Okay. I mean, you definitely don't want a decimal, by the way. I'm kind of brushed over that fact, but this is supposed to be a population of rabbits. You can't have fractional rabbits, right? So you always have to round to a whole number. Okay, so now we have our n naught. That means, so that's what part A was asking. What was the initial size of the rabbit population? There it is. This is the initial size 8 months ago. So now I can write my actual model, my finished model. It's going to be n of t equals 645 times 2 raised to the t over 3. And now this model is ready for all sorts of questions. Okay. So part A here. This is a good question because you have to decide what the initial population is. And the way that's going to work, whenever a problem asks you for the initial population, they're going to have to give you some population at some time, and then you use that. You basically plug those into the model to be able to solve for that missing piece. All right, so part B, which I don't have written down yet. Let me write down the question for part B. Says, blah, 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 blah. Where is the question? Estimate the population 1 year after the rabbits were introduced. Okay, estimate. Okay. Well, we can use our model for this. So once you have the model built, if they're asking for population at some time, that literally just means plug that number in. Except we need to note that A and T, remember earlier for this formula, I said A and T need to be measured in the same time units. 3 is measured in months. I mean, the A that was here, the 3 there, is measured in months. So this is 1 year, so I just need to, first of all, just make sure I know that I'm going to be plugging in 12 for T here. Okay, just so that they're in the same units. So what I'm going to do is I'm going to say n of 12 is equal to 645 times 2 raised to the 12 over 3. And that's, I just need to calculate what that is. In fact, I can even pretty easily say, well, I know that 12 over 3 actually reduces very cleanly to a 4 up in that exponent position. That'll save me a little bit of button punching on the calculator. So 645 times, I need, when you do the calculation in the calculator, you do need to say times. You can't just, sometimes you can just stick the things together, the two numbers together, but not in this case. You need to say times 2 raised to the 4th power. And I'm getting 10,320. And that's the population 12 months from the original point where they were introduced. So that this is 4 months after that data that we were given about the 4,100 rabbits, right? Because there was the initial amount at 645, 8 months passed and we had 4,100, and then 4 more months passed and we have 10,320. But notice the way we did the math here is that we're basing the model off of that very initial size. That's why the whole 12 months got plugged into the model. Okay, so part C, yeah, part C is kind of meh. It says that, you know what, I'm not even going to do it. It says, I'll just talk about it. Part C says to sketch a graph of the rabbit population. Well, here's the thing. All exponential functions, as long as they're not, you know, don't have any minus signs anywhere, it's nothing that flips them over or anything like that, then exponential functions, they all look the same. They all just like go like that really fast, right? They start off kind of flat and then they go off to infinity really quick. So I'll just really quickly graph it in Desmos just so you can see the function. Is Teams going to let me open my tabs? Come on. That is so annoying, covering up the whole. Anyways, okay. All right. Let's see. It's y equals 645 times 2 raised to the t divided by 3. And we're not even seeing it because that's a very huge number, 645. So we got to back out a bit to be able to see it. And the thing is, this is all, we're still not even seeing anything meaningful here, because notice that my independent variable is time. Time does not go negative, right? So I really don't care about anything happening on the left here. I really want to know what's happening on the right. So I need to go all the way up here to that initial point of 645. That's where it's going to cross into positive time right around here somewhere. And like I said, the graph is kind of meaningless. Look, there's that initial value, time 0, time 0, population 645. And then look how fast it explodes. It looks almost, if I zoom out, it almost looks like a vertical line. You can kind of tell it's not vertical up here, but, you know, kind of a meaningless. The only way, if you were trying to like get a nice picture of this, what you would actually want to do is adjust the scales of your axes. Like you would have time going on a normal axis, normally sized axis, you know, like hopefully making each little grid line be like 1 year, or maybe or 1 month, or maybe 5 months, counting like that somehow, you know, some kind of normal small scale. But your y-axis scale, your population scale, would need to be counted in like the thousands, basically, or maybe even the 5,000s, and then you would get a nice shape for the graph. In fact, that's what they did in the picture that they did in the textbook. Their scale for time goes out to 20, and for the population goes out to 20,000. And when you adjust the axes like that, then you get that nice exponential graph shape. But if you don't do that, you're looking at basically a vertical line. It's not a vertical line, but it's, I mean, it's, you really can't tell. Okay. Let's talk about, so we did 2 examples with doubling populations. All right. Now we're going to talk about exponential growth that is relative. The growth is relative to the current population. So it's just another way to model it, and maybe this this might seem a little bit more realistic, because, you know, like a population cannot just increase without bound forever, right? Like it depends on so many other things, and it also depends on the current population size too. Okay. Here is the new model. N of t is equal to, so it starts off the same with an initial value. And now, though, instead of a base 2, because I'm not talking about doubling now, I'm talking about things that are growing relative to their current population. It's going to be a base of e, that special number e coming up again, and then raised to the rt. In fact, this looks exactly like the continuously compounded interest formula. Just replace these with a and p, right? A of t is equal to PERT. That's the continuously compounded interest. Things that are growing relative to their current size, that they're going to be modeled very nicely with a function like this. This isn't even just for populations, right? That like I just said, you can use it for money, for continuously compounded interest. Let me tell you what each of these are, though, in terms of population growth, though. N of t is population at time t, just like last time. The initial size is n naught. That's size at time 0. R is interesting. R is the relative rate of growth. Relative means it's going to be some fraction of the current population, or of the given population, some proportion of the given population. Relative means like in relation to something else, like, you know, for instance, a bug is very small relative to a human, but a bug is very large relative to a single-celled organism or something, you know, like something very small. Okay, so, oh, and time, I left out time. T is time. Okay. And E is the special number, that constant number. So nothing gets plugged in for that, right? There's a button on the calculator for it. Let's practice using this with example 3. Example 3. Okay. So if you're still a little confused about the relative rate of growth thing, we're going to see it in an example here. That'll help. Okay, the initial bacterium count in a culture is 500. A biologist later makes a sample count of bacteria in the culture and finds that the relative rate of growth is 40% per hour. So what does that mean? So before I write the questions, what does that mean? 40% per hour growth rate, relative growth rate. That means after 1 hour, it's gaining 40% of 500. In fact, let me take, just to make sure we're all on board with this idea, I'm gonna go onto a separate piece of paper and kind of draw what's happening here. So at time 0, so I'll say t equals 0, we've got 500 bacteria, or bacterium, I guess that's the way to say it. Anyways, and then after 1 hour, we have a 40% increase. So I'm going to take what is 40% of 500? Well, I just multiply it by 0.40, so that's 200. So that means now I have 700 in here. Just adding that 40% of 500 onto the original 500. Now what happens? Do I just keep adding 200? No, right? I don't keep adding 200. I need to add a 40% now of this. It's always relative to the current population, right? So 700 times 0.4 is 280. That gets tacked onto this. So first there was an increase of 200. Now there's going to be an increase of 280. So now there's 980 in there. And then after another hour, what happens? Well, I need to take 980 and take 40% of that, and that's going to be, so now there's an increase of 392. So let's add that on to, okay, so hopefully you're getting the picture. It's not increasing at a steady rate, right? Because it's not linear, not increasing at a steady rate. It's always gaining. It's gaining speed. It's 40% is the relative growth rate relative to the current population. So that's a picture of what's happening here for the first 3 hours after time 0. Okay, so now kind of hopefully have a better, maybe more intuitive understanding of that. First part A says find a function or model. Find a function, here we go, that models the number of bacteria after T hours. So I'll solve that one first, and then I'll write these other parts. So part A, find a function that models, well, it's definitely going to be n of t, right? N of t. Okay, now I need equal sign. Let's see, what am I modeling it after? I'm trying to follow this setup. N naught is supposed to be the initial size. Well, it literally tells me initial is 500, right? So okay, so that's 500 times, well, I don't really need the times symbol, but whatever, there it is. And then E, that's part of the function model for this relative growth rate, so that's always going to be there. And then R is the relative rate of growth, which is 40%, but since I'm putting it, I don't want to have a percent up there, right? It should be a decimal, so you just take 40%. Remember, to get a percent as a decimal, you just divide it by 100. So 0.40 or just 0.4, and then times T. So that's 0.4, so 4/10 times, that dot is times T. And that's it for part A. Just plugging in those pieces in the appropriate spot. Okay. Part B is going to ask us to use the model now. It says, what is the estimated count after 10 hours? Okay, what's the appropriate way to write this? Well, T is 10. Do I have any funny business going on with the time units? No, everything is given in per hour here, and this is given as hours, so no need to worry about that. So the appropriate way to write this would be n of 10, because T is 10, is equal to 500 times e raised to the 0.4 times 10. So that's up in my exponent up there. So when I run this calculation, I'll say 500 and then times e raised to the 0.4 times 10, close that parentheses, and I'm getting that giant number, 27,299. Hang on. Oh, never mind. I see what they did. Okay. So 27,299. The book rounded to 27,300, which is fine, whatever. They should tell you what to round to in a in like an exam or a homework problem. They'll be more explicit about what you should round to. There are rules that you may know about significant figures, like given in the problem, but the book doesn't even follow that technically, so they kind of just randomly picked a number to round to. I know in any case, though, you would want to at least make it a whole number, right? Because anytime, like I said, anytime you're talking about population size, your answer for a population should be a whole number because you can't have fractional rabbits or fractional bacterium, right? So now with money, it's different. You can have fractional money because cents, right? Cents exist in US currency. But for population, we'll always at least want to round to a whole number. Okay, part C. So hopefully you're seeing like building the function really, I guess, is the hardest part, right? You know, I mean, it depends on how comfortable you feel with these sorts of calculations, but once you get the function, the model, the formula, you're just kind of just plugging in numbers, right? After how many hours, here's an interesting problem, asking for time now. After how many hours will the bacteria count reach 80,000? So this time they're giving me the output of the function and asking for the input. They're giving me that n of t is equal to, like the output here on the left is equal to 80,000. So they're saying you're given an output of 80,000 at some time. Can you tell me what time that happens at? So I don't know time, so I leave it as a t up there. See how I set that up? The n of t, this output gets replaced by that population, 80,000. And now I'm looking for how many hours. I'm looking for this variable t up there. So I need to solve for t. T is embedded in a exponential, rather in an exponent. So I know I've got techniques for this. The first thing is to isolate the exponential function, get anything off of it, right? No addition, subtraction, multiplication, or division. So I do need to divide both sides by 500. So on the left, I've just got e raised to the 0.4 times t. And on the right, what is that, 100? Is that 160? I'll just do it the safe way, divided by 500. Yeah, 160. Okay, and now what I say, okay, I've got everything off of my exponential function. Now I'm ready to take a log on both sides to cancel out the exponential operation here. The log I want to do is the natural log because that has the base of e. First things though, just to kind of clean this up, make it look a little bit more natural, I'm just going to flip it around. Okay, just flipping it around, just to have that t variable on the left. It just looks better, right? Now, in your work, whatever you want to do, right? But for the purpose of a lecture, I have it over there. So I'm going to take the natural log on both sides. So that's the ln, that's the natural log. It's a logarithm with base e because I want to match the base of the logarithm with the base of the exponential operation in order to make them cancel out. And that's what happens. So I'm going to come over here and finish this. That's what happens is this and this cancel out, just popping out 0.4 times t. And I'm going to use an x for the multiplication here, just so you know that that's a decimal point, and then that's the multiplication. I don't want anyone to get mixed up about that. Now on the right-hand side, it's still just some crazy decimal number. That's going to be some wild, irrational number. So I'll just leave it in its nice little compact form like that. I'm not going to start rounding stuff until I'm completely done solving for t. So you see, hopefully, the last thing to do to solve for t is to divide by 0.4. So I'm getting t is equal to, in an exact form, natural log of 160 over 0.4. That's not totally useful here, though, because remember, in real life problems, you know, exact answers are nice in math class. They're nice to be able to write down. They're nice to give to a computer. But, you know, when you want to give someone an answer, how much time will it take for the bacteria count to reach 80,000? You're not going to want to say ln of 160 divided by 0.4 because that's meaningless to a normal human. You're going to want to say, well, that's approximately, and then you would say, so ln of 160 divided by 0.4 I'll just say 12.7 and hours, right? That's how time has been measured in this problem, in hours. There we go. So B and C were different because they both used the model, but part B just asks you for some output at a given input. Let me back up a little bit. They're asking for some output and they're giving you an input, the time. They give you time and ask for population. So you just use the function exactly how it's supposed to be used and you just plug a number into it. Part C is a bit more involved because they're asking for time at a given population. So they're asking you to use the function kind of in reverse. That's what's happening here. That's why there's so much more algebra going on, because you're having to pull out that input value, the t value that's buried all the way up in that exponent position. You're unpacking everything off of it to be able to see what it is at that 80,000 population. Now, maybe in real life, this wouldn't actually be realistic because the bacteria is restricted by the size of its container that it's in or something like that, you know, so there tends to be upper limits on population sizes just based off of resources and, you know, available land and who knows what else, so many things, right? So maybe these models are really good for small numbers of time, small hours, but maybe the model is not so good when you get to higher time. There's a reason people get paid a lot of money to think about this stuff a lot, right? There's a lot going on. We're just really just scratching the surface here, but lots and lots of interesting questions. Okay, part D, again, is asking for a graph. It's honestly just kind of useless to look at, in my opinion, unless you really mess with the scales of the axes. Because look at the difference in these things. T is only like 13, roughly 13 here. That's a 2-digit number at an output of 80,000. I mean, just imagine how big your y-axis has to be, your vertical population axis has to be versus time, right? So I'm not even gonna graph it in Desmos. Okay. Let me see where we're at. Let me see what problem I gave. Okay, well, got 2 more. Wait, how many more? Yeah, I've got 2 more examples I want to look at that deal with these same 2 formulas, either a doubling formula or a relative growth rate. So next time we'll do, oh, by the way I numbered these examples, they're from the text. So you may have noticed I started at example 2. They're from the text if you want to go look at them. So I'm going to work out on Wednesday example 4 and 5 from the text. And then that'll be it. And then we can spend the rest of Wednesday reviewing, or just review on Friday. There's not too much to review, but I'll explain that, because I'm telling you exactly the particular things I want you to be able to know on the final exam. I'm not just saying like, oh, just know all of it. All of it has the potential to be there. I'm narrowing the scope a lot there, so we won't need honestly more than an hour to review probably. Okay, so if there are no questions, we got a few extra minutes, but if there are no questions, you guys are free to go.